So I don't know about you, but this semester has been pretty exhausting. And if you're taking a lot of these summer courses, I can imagine that you are just about fed up. So we only actually have two conceptual topics left, fortunately. And that means that assuming I can actually make it through all the slides for each topic in only one video a piece, there's only two of these lectures left. And then I'm also going to post a third thing, which is a demo of how to use Python with Postgres, which we'll need for assignment 6. And if you're just about fed up with writing select statements, I've got some good news, which is that we've reached the top of the mountain as far as select statements are concerned with assignment 4. We'll need a couple of select statements for assignment 6, but they'll be relatively straightforward. And assignment 5 will actually be a written assignment in the vein of assignment 1. So if that appealed to you, then we're going back to that. So the first of our remaining two topics, which is carrying on with our discussion of the ACID framework, is isolation. Because obviously that's one thing we don't know enough about already in 2020. And so we'll go back to our example with the flights to book, again, just to rub it in that we're not booking any flights anytime soon. I actually think, I like to believe that our discussion of atomicity and consistency largely solve the problems that can show up here. The discussion we're having of isolation is not really a performance issue. It's about solving a practical problem, though. The assurance of atomicity and consistency is absolute. If we define, for example, that flights can have have to have at least 0 available seats, they can't have a negative number of available seats, they can't be overbooked, then we should assume that holds absolutely. And if we define atomicity of transactions, then we assume that if both travelers try booking their flights and there's a problem with one of the bookings, that either the transaction succeeds completely or completely fails. So atomicity and consistency have actually given us most of the guarantees we need. But we have to talk about, well, what happens if we have two transactions that are running at the same time? And what I want is to guarantee that if I've got multiple users, and I'm going to use the term user and transaction pretty much simultaneously. We'll mostly talk about multiple transactions. If multiple users try to modify the same data, and that actually modify or read the same data, then I need to make sure that the operations they are doing do not interfere with each other. I need to create the appearance of isolation. And I don't consider this to be as important as atomicity and consistency because there is something we can do to guarantee isolation in all cases, even without complicated mechanics. It's just that it results in the database being much less useful, which is that we can make sure that only one transaction can ever use the database at a time. That's how we can guarantee that transactions are isolated from each other. So the assurance that we want, and I'll keep refining our definition as we go here, the assurance that we want is that even if the database lets multiple people open transactions at the same time, so you run start transaction and I run start transaction, and then we each run a bunch of insert statements and a little while later we run commit, then we were both running our transactions at the same time. And of course, our transactions either succeed or fail. And maybe one of our transactions succeeds and the other one fails because something that the other person did affected the validity of the operations of the transaction that we're running. That's all fine. That's guaranteed by atomicity. What I need is from my own point of view, if I open a transaction on a database, I need the perception that my transaction is the only thing running at that time, that my transaction is isolated. It's a weird thing to require, and obviously it's easy to guarantee that if your transaction is the only thing that's running. So there is a way of assuring isolation. It's to actually isolate transactions and make sure that only one transaction can be using the database at a time. But we'll see that that's not very practical. So we need a practical solution here. So we're not talking about this idea about guaranteeing consistency. Well, yeah, consistency, the C in the ACID framework, that takes care of the problem of enforcing all the constraints. We're not threatening consistency here. We're trying to make sure that if we want to allow multiple transactions to happen at the same time, we can do so without compromising on consistency. So suppose that our two travelers book their itineraries as follows. They first do a pre-check, just to avoid extra work. They check that all the flights are available. So traveler A checks all of their flights and makes sure they're available. And then it turns out they are. And then Traveler A books all their flights. And then at some time in the future, maybe time 4, maybe time 4000, Traveler B starts making their bookings. And they discover when they do a pre-check that they can't. One of the bookings can't be made, so they just give up. The bookings, they reject all of the bookings are canceled. The itinerary is simply not booked. Well, that's great. Those two transactions both ran. One of them failed, but remember that we don't regard the failure of a transaction as a failure of the database. Sometimes transactions fail because sometimes you can't achieve consistency if the transaction is allowed to succeed. That's fine. We want to make sure that if the transaction can succeed in the current context, that it does, but it's no big deal if transactions fail. That happens sometimes. And it's bad news for the person running it. That's, I guess, from our point of view, that's their problem. So this example here is what we're going to call a sequential or serial schedule of transactions. All of transaction A runs, and then all of transaction B runs. In this case, transaction B ends early, but they were never running at the same time. And so it's a serial schedule or a sequential schedule of transactions. And we can see they're never going to get in each other's way directly, but because they never are active at the same time. It's true that something that the first transaction did affected the second transaction, but that's just because the database got modified and the state of the database was different at the end of one of the transactions. That's also no big deal. We expect the database server receives lots of transactions from lots of people, and it'll start them, I guess, in the order that they come in. And so it makes sense. If you book your flights early, you're more likely to get a seat. In a large-scale database system, and I'm going to have to walk this remark back in a minute, we have to be very careful about what we say about this word. In a large-scale database system, we do want to begin thinking about, well, we have this large database system on a server probably because a lot of people need the data. So if that's the case, we should reasonably assume that eventually we'll have a system large enough that there are two users running operations literally simultaneously. So at time step 1 on two different processors or two different nodes of the cluster, two distinct operations are happening. And so in this example, both travelers book their flights literally simultaneously. At time 0, they both do a pre-check, and at time 0, both pre-checks pass, because at time 0, there is an available seat on each flight. And then at time 1, Traveler A books their flight, Traveler B books theirs. At time 2, Traveler A tries to book their flight, but by then flight 302 is full, and so Traveler A's transaction has to be aborted and rolled back, whereas Traveler B can continue booking. And so here, Traveler A's transaction is rolled back, and then Traveler B's actually gets entered into the database. And so this means, obviously, if both are happening at the same time, Traveler A or Traveler B could end up out of luck. Their transaction could start, and then things could change in the middle, and it could have to be rolled back. Now, it's worth considering, if you notice, the pre-check was sort of useless. The pre-check, we can think of it sort of like an optimization here. It's useful to do a pre-check, I guess, assuming it's fast, because it means we don't waste time trying to book an itinerary of 40,000 flights if flight number 39,999 ends up being full. Okay, but on the other hand, we could just try booking. We could just start booking flights and then assume that, hey, if we make a mistake, the transaction will be aborted and we will roll it back. So why bother with the pre-check? And so I'm going to view the pre-check here as an optimization. Maybe it's helpful, but who's to say, really? I mean, like, we're not the ones writing the database code, so how do we know if that pre-check actually takes longer than it would just book the flights? So we'll just abandon that. Instead, if you want to book an itinerary, you just start sending in bookings. And you assume that if the bookings don't work, your transaction gets completely rolled back and none of the bookings ever happened. Now, here's the problem. So concurrency is one of those words where as soon as it shows up in the context of a problem somebody's having, like this problem seems to be caused by concurrency. Everybody these days will say, oh, well, of course it's concurrency, typically. You can't do two things at once. People don't like concurrency because they remembered CSC 360 and they remember having to do their train assignment or whatever the one about threading is, and they know all the ways that can cause trouble. So you might say, well, the reason this is going to be a bit of an issue is because we shouldn't let two things happen at once, right? Why should we run a database where two things can happen at literally the same time? Okay, well, for one thing, we do have to do that because there are databases that need to deal with billions of operations per second and could be distributed over continents. Okay, but even if we ignore that, then there's the issue, which is that even if only one operation can happen at a time, what if transactions can be interleaved? So here we're back to having only one operation at a time. And pretty much for, I think, the next 100 slides, I'm going to talk about a processing model where one thing happens at each time. We don't have multiple cores, we don't have multiple threads. It turns out that what I discuss will be applicable easily to multiple cores and multiple threads, but I want to avoid scapegoating this concurrency with a capital C, the kind of concurrency you'd see in CSC 360, threading or multiprocessing, because it's too easy to blame that. It's too easy to scapegoat that. So let's think about this. Traveler A begins their transaction and they book their first flight. And then they go take a break, for all we know, right? It takes them a minute to send in their next insert statement. Or maybe they go get a coffee. Who cares? They open a transaction and do something. And then Traveler B opens a transaction and does something. Now, I said earlier, we could disallow this. We could say, hey, if any transactions are open, nobody else is allowed to open a transaction. But you might be able to see why that's not a sustainable model, right? Maybe my transaction has 4 million things in it, and it's going to take 5 days to run. Or even worse, maybe I work for a competing airline, and I open a transaction and then just leave. I just leave a transaction hanging because I know nobody else can use the database. There are lots of reasons why it's useful to let two transactions run interleaved. So not necessarily simultaneously, but with the operations interleaved between them. And of course, more importantly, in the best case, maybe, 100 transactions can run at once and none of them ever need the same data. So it's fine. They never interfere with each other. The problem is transaction for Traveler A and Traveler B here, they do get in each other's way. Traveler B books flight 302, and then Traveler A tries to book flight 302, and there's a problem. And Traveler A's transaction has to roll back. So this can happen, and I mean, fair enough, the transaction fails. We need to talk about the implications of this behavior. So one remedy is just to say, anybody, as soon as you start a transaction, the whole database is locked down. Nobody can do anything until that transaction is over. I just explained why I think that's a bit short-sighted. And even if we ignore the case of actors in bad faith, what if I'm running a I don't know, what if I am, you're booking your flights, but over here, I run a transaction to add all of the flight data for the next 2 years to the database. That might take a long time. I need the database to still be accessible during that time. So certainly locking stuff up is a good way of avoiding concurrency problems, but we want to be a bit more fine-grained with our locking. Maybe I want to lock up a single row or a single piece of data, or maybe just one table. I don't want to just lock down the database. I want to allow multiple users to send in modifications at the same time. So here's what I want. I want to have the assurance of isolation. And as I said, I'm going to keep refining that, but in the context of a transaction, an atomic transaction that's running, what I mean by that is the statements between the words start transaction and commit, or rollback, but usually we assume our transaction can eventually commit. I want it to be the case that between start transaction and commit, from the point of view of the transaction, so that means any modifications it does, any inserts or selects, it appears to that transaction as if it is the only thing in the universe. There could be other transactions running in the background too. As long as they don't do anything that I can see in here that affects what I'm doing in here, that's fine. That is isolation. It is the appearance from the inside of a transaction that no transaction is running at the same time. So the inability for this transaction to observe the changes being made by some other transaction based on what it's doing. Now, the issue with isolation is that there's a lot of layers to it. And I want to talk from the point of view of 370 just at the mechanisms used inside the DBMS. So the DBMS itself is a piece of software, and it's written in some language, probably C or C++ for most of it. And of course, that runs on an operating system, and it might use threading or multiprocessing or be on a cluster over a network. We can't talk about that aspect, about the threading, because that's 360 material. And not only do I not want to step on the toes of 360, but also many of you haven't taken that yet. And if you are currently taking it, you don't want to talk about threading anymore, which is also fine. The other thing is that if we talk about networked databases over a network, that requires networking knowledge. And really, it turns out that what we care about isn't threading, because that is a 360 topic. You'll learn about that in 360. We care about how we can enforce isolation, assuming very basic ideas like suppose we're allowed to lock a row of a table to modifications. How do we do that? I don't know, mutex, semaphore, whatever. That's somebody else's problem. Let's instead talk about the mechanisms used from the point of view of the database. How they're implemented, that can be covered at, somewhere else. Now, there are higher level courses that get at this, and they also get at things like distributed systems for databases over networks. It's just that from the point of view of just 370, we need to talk about isolation, but we're going to talk about it pretty conceptually and at a very database focused level. What I'm going to talk about then is transactions that just read, modify, and write individual data elements. Whether those be rows of a table or a single column inside of a row, it turns out we don't care that much. It's just about whether two transactions need to modify the same thing. So again, just to remind ourselves of this, transactions sometimes succeed and they sometimes fail. It's certainly, it's not ideal if it fails. We as people discussing isolation shouldn't feel guilty if transactions have to fail. That's the user's problem. The idea is the database system is the gatekeeper of certain assurances. Assurances like that the constraints will always be enforced. Assurances like that operations like transactions are atomic. The database system really doesn't, it's not really the database's business whether you're sending in transactions that make any sense. So if you send in a transaction that fails, that's just too bad. We would like it if your transactions succeed, but it's fine if they have to fail. We shouldn't feel guilty about that. So the goal of these mechanisms is to make sure that we can keep the database in a consistent state. We already have that assurance from consistency. Our hope is that we can find isolation mechanisms that are more advanced than just constraining the database to running one transaction at a time. I want to let the database share its resources among multiple transactions as long as I achieve isolation. And so if I do achieve isolation, which of course I have to if I want to be ACID compliant, then the database will always be consistent and no transaction's output or the results of whatever it does will differ from the results of if it ran only like by itself on a database with nothing else running at the same time. So I'm going to use this little tableau style to represent transactions. Here I have two separate transactions and we'll assume each transaction is being sent in from some separate source. T1 and T2 are unaware of each other, and we want to keep them that way. They may run at once, but they are unaware of each other. So I send in T1 in this order, and notice how I'm using very simple operations here. I don't want to talk about insert, select, and update because a single update statement could modify a huge number of rows of a table. A single insert statement, if we consider the effect of stuff like triggers, could end up inserting and deleting rows from multiple tables. I want to be very careful, so instead I'm going to talk about the low-level operations that are performed on individual data elements, whether those be a row or a single value inside of a row. Now, it's true that this representation can be generalized to insert statements because logically, even if we ignore constraint triggers and things, an update statement, for example, would be look at the row, decide if it meets a condition, perform some operation on it, and then put it back in the database. So this still applies. It's just that we don't want to talk about high-level statements. We want to talk about individual modifications. So if I'm the one writing the commands for T1, I'm sending them to the server, or I'm performing this set of operations. The read and write operations are being done by the database. If I read the value of X, the database will then send me the value of X, and then I've got my own personal copy of X, and I can modify it like this. I can take my personal copy and I can send it back to the database here, write X. So the idea is that the database receives these transactions, and we'll see in a few minutes that we don't even care what T1 is doing with the value. We just care when it's reading and when it's writing. Those are the only things that the database actually sees. So these things happen, they happen in this order. And our goal is to enforce isolation, which is that from the point of view of T1, it is the only thing running right now. One thing that's going to be a sticking point that I've noticed in the past is it doesn't matter what order the transactions run in a macroscopic sense. So suppose that you were the one writing the transaction T2. You knew nothing about T1. And you send in the transaction T2. Do you know if T1 has already happened or not? Well, of course not. T1 could have happened yesterday. T1 might not be sent in until next week. Who cares? You send this in and you assume the database is in some state when you begin and that the state is the same until you're done because you want to believe you're the only thing running on the database right now. So it's not significant when the other transactions ran. The concern we care about is, from the point of view of an individual transaction, every other transaction either has to have already finished or hasn't started yet. That's all. There's nothing wrong with the other transactions happening first or happening second. But if you're inside of a transaction, you want to act under the assumption that every other transaction that could ever exist has either already happened or will happen later and is not concurrently executing with your transaction. So suppose we work in a very limited model where only one processor, and just to be clear, I'm going to use that to mean thread, only one thread is running at a time. So one operation can be performed in any given time step. And we'll also assume that these values x and y are single integer values. Now again, x and y could be strings or entire rows or even tables or something, but we'll just assume that they are single numbers because we want to do numerical operations on them because those are easy to think about. So if T1 and T2 are running separately, I guess, they would each have their own copies of x and y that they use. So T1 reads x, which means at this time step, the database tells you the value of x is 0. And then you keep that as your own personal copy of x. A couple time steps later, you write the value of x, which means you take the value and you send it to the database, and then it gets updated in the database. This is what the database actually contains. So T1 and T2 are both running, and we could use this scheduling, so time goes downwards here. So time step 1 is the first time step to run. And this is one ordering of operations where transaction T1 executes entirely before transaction T2. This is that sequential or serial schedule of operations. And we can see that when we're done, and just to be clear, the values that I'm showing here for x and y are the values of each thing after that time step. So you can see here, after the time step 1, T1's value of x is 0. After time step 2, when it adds 6, the value is 6. So this is the serial schedule where T1 finishes before T2, and the final result of both values in the database is 7 and 1. That's the slide it's just saying what I just said. It's a serial schedule because all of the operations for a transaction run without any other transactions operations being interleaved. And the way you should view that is they all run in a row. T1 is a single block of operations. I suppose it would be fine if there were like a white space in the middle, but no other transaction is allowed to get in the middle of T1. And the same with T2. Any schedule of operations that observes this constraint, where each transaction is a solid block, is called a serial or sequential schedule. Although I will keep, for the rest of this example, I'm going to keep saying serial schedule, and it'll become clear why in a minute. Now, suppose you send in T1. I mean, you don't know that T2 exists, so how do you know whether T2 has happened yet? It could be you send in T1, and you're the very first transaction to execute. And so when you're done, the values of x and y are 6 and 0. But it could also be that you send in T1 and it happens that T2 is already executed. That's no big deal. That's not an isolation problem. Obviously, whenever you run a sequence of operations on a database, there's already data in the database. You have no idea how it got there. I mean, like who modified it before you. You just work with whatever's there. That's the point of having a database. So you read the value of x and it happens to be 1. Okay, great, fine. I mean, obviously, other stuff could have happened first. So that's no big deal. That's not a consistency or isolation problem. Either of these orderings is perfectly fine because it's a function of outside factors, like when the transaction T1 gets to the database server. So we assume either of these is perfectly valid, which means depending on the order of your transactions, the final result could be 7-1 or it could be 7-10. Those are the only two options, though, if the transactions have to run in a serial order, because either T1 goes first or T2 goes first. It's true that I suppose there are some transactions that need to go first or something, so maybe T1 is designed to only ever run first. But if T1 is supposed to go first, then how did T2 get there so early? Well, maybe T1 was delayed in transit, who knows? If T1 can't work properly unless it runs first, then I suppose T1 has to abort, because T1 unfortunately had to go second here, because it didn't get there in time. And it's sad if T1 fails. It's not our problem. We shouldn't feel too guilty about it. The people sending in T1 should have known that before they let T1 wait too long before getting there. So here is the idea. these orderings we just saw, the two possible serial schedules, reflect what would happen if the database only let one transaction run at a time, right? They're the serial schedules where each transaction gets to own the database during the time that it's running. We know that there are multiple valid serial schedules for a given set of operations because it depends on when the transactions get there. That's fine. What we want is, given any set of transactions, I want to find a way of, even if the transactions are coming in interleaved, even if I get this from T1, then I get this from T2, then I get these two things from T1, then I get these three things from T2, even if I'm getting them intermittently, I might have to delay one of the transactions a bit or something. I want to find a way of scheduling the operations so that the transactions can be done as concurrently as possible, but also such that the outcome, the result that I get at the very end, is identical to some serial schedule. In other words, from the point of view of each transaction, it is running on a database where nothing else is running at the same time. It behaves as if it owns the database during its execution. And so just, I'm going to keep emphasizing this. The exact ordering that the transactions occur in the serial schedule is none of my business. I don't care. I get the transactions and I run them. In a serial schedule, I get some result where each transaction gets to own the database. The fact that T2 went first here is somebody else's problem. It has to do with factors that are outside of my control. If, as I said, if we care that one transaction goes first, we have to either abort the transaction if the order isn't obeyed or add extra constraints, which are not, fortunately, the isolation side of the ACID framework. So basically what we care about here is that we'll see in a minute, it's fine if we allow certain transactions to mesh together if they don't work on the same data. We don't want a transaction to be working on the value of x. So for example, I pull in the value of x and it's 1. And then I'm going to modify it to 7. And if this is the only transaction that's running, then yeah, it makes sense. X was 1, I add 6, then I get 7. What I don't want to happen is somewhere in the middle here, the value of x gets changed, because that's not consistent. If I'm the only thing running on the database, how did the value of x get changed in the middle of my operation? That doesn't make any sense. We want to avoid that. We want to avoid two transactions interfering with each other in some way. Let's look at this schedule. This is not a serial schedule because obviously the transactions do not run as one long block of operations. I run part of T1, and then T1 takes a break, and I run part of T2, and then I run part of T1 again. Notice that the result of this schedule, and maybe it's obvious sort of why this is the case, the result of the schedule 710 is the same as the result of this serial schedule. So even though things happen in a different order, the result is exactly the same. So what happens is T2 works on Y, and then it writes the result out to Y. T1 then begins working on Y, and the result it gets is the result of T2. And that's fine, because I guess from the point of view of T1, it looks as if T2 is already done. Okay, then T1 finishes working on Y and puts the result back. Now T2 picks up and reads the value of x, and then writes the value of x back, and then when T1 resumes, it reads the value of x, and it gets T2's output, which is fine again, because T1 already suspected that it was running after T2. So from the point of view of T1, it's running second, which is fine, because transactions can run in any order. And so this is equivalent to a serial schedule. It's equivalent to the schedule where T1 actually does run second. And we call this a serializable schedule. Now we'll see that we need a bit of a stronger definition because there's some weird things that can happen with just the word serializable. So a serializable schedule is one that has the same final result as any serial schedule. It doesn't have to be any particular one. There could be lots of different serial schedules. The more transactions you have, the more different possibilities there are. If your schedule is equivalent to any of those serial schedules, then you have a serializable schedule. And this is our ultimate goal. We want a serializable schedule. You give me a bunch of transactions that send in their operations interleaved. All I want to do is guarantee that the ultimate result of those operations is identical to any serial schedule. So what about this one? So notice how here I'm doing the operations in T1 and T2 in the opposite order, but they're still interleaved. So here T1 reads X and then writes it, and then takes a break, and then reads Y and writes it. The result is still 710, which is the same as one of the serial schedules from earlier. It's the same as this one here, where T1 goes second. And you might notice that here, yeah, T2 works on X, then T1 works on X. T2 works on Y, then T1 works on Y. So as far as T1 is concerned, it is running after T2. And so the result is the same as a serial schedule, so it is a serializable schedule. And it's true that if you want to tell if a schedule is serializable, you could run it yourself, get the final result, and then try every possible serial schedule to see if any of them match. That would work. That's not great. We'll see that there's some ways around that in a few minutes. So yes, it is serializable because this serial schedule produces the same result. What about this one? So here, the operations have been divided up in a very strange way. So T2 starts, it does a bunch of stuff, it modifies X, then it reads Y. And then it takes a break. And of course, its own internal value of Y is kept around. When it picks up again, it modifies its internal value of Y and writes it back. And that's fine, because nobody needed Y in the meantime, so there wasn't ever any interference. In the meantime, T1 worked on X, and T2 didn't need X in the meantime either, so it really wasn't a big deal. And then when T2 was done with Y, then T1 begins working on Y. And we get the same result as the serial schedule from earlier, and so it is a serializable schedule, even though I broke up the operations in a funny way. Now this is a proof of concept, but the reason why this kind of distribution of operations makes sense is that when you're running a transaction, it could be full of select and insert and update, and in the middle of it, you could be taking the results of the previous. So for example, you ask me for the value of Y, and I give it to you. And then you do some processing on your end, and it takes you a while to begin to pick up and do more work because you had to do some more processing. That's why you took a break. It's good for the database to be able to fill that time doing some other work. And in this case, because you're working on Y and T1 is working on X, it's easy to find a way of letting you both work on the data at the same time because the pieces of data you're working on don't conflict with each other. Okay, what about this schedule? So this one's a bit worrying here. So here again, I read Y and then I take a break. Okay, so now my internal idea of the value of Y is 0. Okay, so then in the meantime, T1 reads and works on X, fine, and then it reads Y. Okay, so now both T1 and T2 do actually have the current value of Y at this point. Even though T2's value of Y was read a few time steps ago, the value of Y right now is 0, which means that the value of Y does match up in the database to both T1 and T2's idea. The problem is what happens next. So what happens next is T2 modifies Y and stores it back. And then T1 goes back to work. T1 begins manipulating what it thinks is the value of Y. But as of here, the value of, or actually it's here, as of here, the value of Y in T1's conception is different from the database. T1's value of Y has gone stale. So when T1 modifies the value of Y, it's modifying the value of Y from before T2 touched it. And that's a bit difficult because you might notice T1's value of X is the same as the output of T2. So T1 might think it's running after T2. And yet, when T2 finishes with Y, T1 never sees that. So T1 is somehow running both after T2 and before T2. So the conflict here is the value of Y. The value of Y that's modified by transaction 2 is never seen by transaction 1. I guess this should say transaction 1. And so there's no serial schedule that would ever produce this. In a serial schedule, either T1 sees Y after T2 is done or before T2 is started. They don't end up interfering with each other in the middle. And this result, if you go check, doesn't match up with any serial schedule. Okay, what about this one? Okay, so this is actually the same problem. It looks less menacing, but it's the same issue. So T2 modifies X, and then T1 works on X. So as far as T1 is concerned, it's running second. But yet, T2 picks up and begins working on Y when T1 is done, which means that T2 is running both before and after T1, and T1 is running both before and after T2. That would never happen in a serial schedule. But is the schedule serializable? And I mentioned this is why the word serializable is a bit tough for us. So what does it mean for a schedule to be serializable? It means its effect is equivalent to a serial schedule. Its effect is X equals 7, Y equals 1. Let's go look at our serial schedules. Okay, so there's one of them. X equals 7, Y equals 10. And here's the other one. X equals 7, Y equals 1. So for some reason, 7, 1, that is a serial schedule. We go back over here. This schedule is got a lot of issues, and yet for some reason it is serializable, because it does, even though it does some weird stuff, it does actually give the same result as a serial schedule. Now I actually know why this is deliberate. The reason is because y is being multiplied by 10 here, so that's multiplication by 0. So the value that y ends up with is the same as its initial value. So as far as t2 is concerned, it is actually running first. It is true t2 is actually getting the output of t1 here, but the output of t1 happens to be the same as the initial value. So t2, as far as it's concerned, actually is running first. So it turns out this is serializable on a funny technicality. And the technicality is this operation here seems to be just amenable to that kind of transformation. If this were a plus sign, that would not be a serializable schedule. Because if this were a plus sign, the result that we end up getting here would be 10, and then y ends up equaling 10 here. And then we read y, and then y is 11, and we can see that 7, 11 is not the result of any serial schedule. So that's a coincidence. So here's a new set of transactions. I've changed the operations that are being done. In this case, T1 is only doing multiplication, and T2 is only doing addition. The schedule, literally this schedule is obviously serializable because it's already a serial schedule. This is a serializable schedule too, because note the result, 1, 1, and 1, 1. So it's serializable because it produces the same result. What about this one? So here, T2 works on X, T1 works on X. T2 works on Y, T1 works on Y. Is this schedule serializable? Turns out the answer is yes. Maybe you can see why. Even though they're interleaved, the interleaving doesn't result in them ever needing to conflict with each other. T2 always comes before T1 for the various pieces of data that both of them end up working on. So T2 comes first for X, T2 comes first for Y. So it is equivalent to the schedule where T2 just comes first. What about this one? So we've maybe seen, once we have these slides with the serial schedules, we have a bit of an easier solution method here. We know what both serial schedules produce. One of them produces 1, 1. The other one produces 2, 2. So is this a serializable schedule? Nope, it isn't, because it's not 1, 1 or 2, 2. And with two transactions, there are only two serial schedules. So neither of the available serial schedules give me the same result. Now, you hopefully already alarm bells are going off and you're thinking, how am I supposed to compute this? Like, do I really want to go and figure out the final result of two transactions if I have to do this? Yeah, that's one of the many problems with this analysis. We actually have to simplify a lot of things and create more conditions because we want to do our analysis symbolically. We do not want to actually have to compute this tableau of time steps. So here we have two transactions, and only one of them works on Y. So T1 does a bunch of work on X. You might notice that it reads X twice. That's fine. I know it seems redundant. Why would T1 read X if it already has the value of X? Keep in mind that maybe this read-write group is the result of one insert statement, and this read-write group is the result of another. They both need the same data, so they both read it. They don't know of each other's existence. So two separate insert statements may not know to pre-cache the data between them. So it's reasonable I might read X 2 times. So because an insert statement could have a nested select or something. So T1 works on X, T2 works on X, but also works on Y, but nobody else ever touches Y. So my question is this serializable? Most of T1 happens first. So before T2 touches X, T1 does all of its work. And then T2's operations on Y are strangely scattered throughout the schedule. But we'll notice that the result is the same as the serial schedule, because the operations on Y are independent from everything else. They can happen whenever. As long as they still happen in this order, they can happen whenever. So even, and the goal of this example is to illustrate a few things, but one of them is, notice that this is a bit like, why are we putting one operation in the middle? That's fine. I mean, who knows why, but it's fine to do that. As long as the result is serializable, it's fine. And it turns out, yeah, it is serializable, because even though we read Y and then take a long break, nobody needs Y in the meantime. So no big deal. Now, on the other hand, this schedule, where I've just shifted everything down by 1 pretty much, so I read and write Y. So now T2 is now done with Y. And then down here, I read X, and then I take a break for a minute. And in the meantime, the value of X in the database changes. And then I begin working on the value that I had, which has gone stale. So maybe it's clear that the stale value of x that I have here is going to be a problem. But I want to illustrate something else about transactions that's really worrying here, which is that if we have isolation, so if the transactions truly are running one at a time, and that's what we want, the isolation is the property that from the point of view of any transaction is the only thing being executed. If T1 is the only thing executing at a time, then either you run before T1 or you run after. If you run before, the value of x is 0. If you run after, the value of x is 1000. Under no circumstances will you ever see the value that's written here, because T1 writes it and then it changes it. Nobody in the outside world will ever be aware that x was equal to 100, because under isolation, either you run before or you run after. You're never allowed to peek at the value in the middle. So what's worrying about this is that some other transaction sees this value 100, this internal value that nobody else is supposed to know about. That not only does that create the incorrect result, that's an example of one transaction breaking into another, where isolation is not achieved. The only way T2 could see the value 100 there is if T1 happens to be in the middle of its operation, which of course doesn't make sense. If T2 was the only thing running, which is what we want to, the behavior we want if isolation is achieved, then T2 would never be able to see another transaction that's currently in progress. So this is not serializable, and even if we ignore the serializability, it obviously breaks isolation, and so we don't want this. Okay, and then before we can begin simplifying things down, we've got one more example to prove a point. Let's take a look at this. I'm going to draw a line here, I guess. So transaction 1 reads and writes y. And then transaction 1 finishes, and then eventually transaction 2 reads x and reads y. What I'm observing here is, look at this read y command. If I were to move that up to here, that would have no effect. That'd be fine, because obviously this read x doesn't have any effect. The write x has no effect, so I could move it up to before that. I could move it up to this line, and it would be no big deal. The value of y is never going to be touched between when T1 finishes with it and when the read is already scheduled. So I can move the read as far up as I want until I hit this line, until I hit the last time that the other transaction modified that value. So that's one thing to think about. Now, in this serial schedule, I mean, if I got transaction 2 at the end after transaction 1 was done, then of course I'd start running it here. But maybe transaction 2 was waiting in line. And if that's the case, maybe there are some parts of it I could do a bit earlier. I guess it makes sense. If this command got to the database server, I don't know, somewhere up here, I guess I have to keep it waiting, because transaction 1 seems to still be working with x. I have to wait until transaction 1 is finished with x before I can let anybody else touch it. But transaction 1 is actually finished with y at this point. So as soon as it's finished with y, I'm allowed to let other people begin looking at the value of y, because transaction 1 will never touch it again. So the first simplification. So those last few slides were proving a bunch of points that we'll unpack in the next 60 slides or so. The operations that I'm doing on these things, so y equals x plus y, okay. This is irrelevant to the database. The database only cares what you're reading and what you're writing. It doesn't care what you're doing with it in the meantime. So why do we draw it on the schedule? Let's just draw that T1 reads y and writes y. And we'll assume that we have to make one extra assumption here, but basically we do this because the database doesn't care what you're doing, like z equals x plus y, whatever. The database cares when you read a value and when you write a value. So we will discard the information on the actual operation that we're doing. We'll just model it in terms of reading and writing. This requires us to make one extra assumption, which is, okay, so somewhere in here we probably had, z equals x plus 1 or something. The problem is, when you write the value of z, I don't know where you got z because I discarded that. I no longer have information about what you did with z. So I have to assume that whatever you write back to the database could have involved every single value you've read so far. Even if it is just z equals 6, I have to assume that the value you're writing for z could have required information about x and y. So that's one thing I have to begin assuming. It's true that that assumption requires stronger conditions, but it does allow us to really strip down the set of operations that we care about. Now all we care about are reads and writes. And so notice that in this example, the read y instruction here can actually be moved up freely. If I'm only allowed to do one thing at a time, I could move read y up here and then move the write x down, and that's no big deal. Y hasn't changed because of this. And I could move the read y up here, and neither of these change y. In fact, actually, even though T2 needs y as well, none of them ever touch y. So none of these commands in T2 ever modify y, so I can read y wherever I want, because y will never change. And just like in that previous slide, this is going to be significant later. It turns out that two reads will never get in each other's way. Even if both transactions need to know the value of y, as long as the value of y isn't being modified in the meantime, the time at which I read the value of y isn't significant. Now, it is, of course, true I could not move the value, the read y, down here for lots of reasons. One of which, I mean, the biggest one is obviously once I've modified y, the value of y has changed. Now, on the other hand, if we take a look at this write x, so we're going to see in a minute, we do not like reordering a transaction's operations. We assume a transaction comes in a specific order and we have to go in that order. This is just a conceptual example. If I take a look at this write x, I suppose if the transaction would let me, I could put it up here. And I might even be able to put it before the read y, if that makes sense in the context of the transaction. But I certainly couldn't put it before this write x unless I put it all the way up here. In other words, unless T1 just came first, if I put the write x above the write x in T2, then it's getting in the way of these two operations in T2, or these two operations in T2. So you have to be careful about that. So there are cases where we can move stuff freely. Usually reads can be moved much easier than write operations. We have to be very careful that if we're moving a write operation, that doesn't get in the way of another write operation, or in fact in the way of any read operations. So therefore, if I take a schedule, there are certain changes I'm always allowed to make, and they have to do with whether certain conflicts occur. So here, I'm allowed to go from this schedule where I read and write y here to this one because I can move these two up because neither of these involve y. So there's no reason why they'll get in each other's way. In fact, I could even move it further because, again, this read y is not going to get in the way of this read y. But the write is something that I can't move up any further. Because this is going to get a bit busy because we're going to need more than two transactions eventually, I'm going to use this notation. The book also uses this. The chapter in the book about this is great. The book is pretty lucid on this subject, which is good. It also talks about the way this factors into SQL. There aren't many SQL statements you need to specifically actuate isolation, because isolation should be handled by the database, but there are a couple that you can use to optimize it, and the book does talk about those too. So I'm just going to use this notation. I'm going to refer to a read as R and a W as W, a write as W, and I'll use this function style notation. Instead of writing read Y, I will write RY. And I'm going to label every read operation and every write operation with a number, which will be the number of the transaction. So in this vertical schedule, everything in column T1 will be subscript 1. Everything in column T2 will be subscript 2. So R2X means T2 reads X. The reason why I like this is that now I can write the sequence of operations, because in this model we're not letting two things happen literally at once. I can write the schedule of events as a linear sequence like this. So R2X, R2Y, that's these two, and then R1Y, W1Y, and so on. So I can write it as a left to right linear sequence. So the question basically is this. If I hand you, it doesn't matter if one of them is a serial schedule or not, although ultimately I care a lot about serial schedules. If I hand you two schedules, like this one and this one, the question is, when do two different schedules with the same transactions, so we assume in this example that the set of operations in each column is the same, when do two transactions with the same operations have the same, two schedules of those have the same outcome? So this is the same set of operations, but they've been reordered in some way. And we've seen that there are a lot of quirks. So we saw that example earlier where something weird was going on, but the ultimate result, was still the same as a serial schedule. That's a bit scary because that requires us to know a lot more about the data than we know from this representation. That's what the slide is pointing out. We actually have to know a lot about like for example, all of these reads and writes could be writing the value 0. in both transactions, in which case we could reorder them however we want and nothing would make any difference. And so even if we knew that, like even if I told you in advance exactly what each transaction did, it's really tough to know what you can reorder. That can require a lot of computational power far beyond what a database would actually have at its disposal. What a database is dealing with is it's receiving, it might have 10 transactions open with different users, and they're just sending in commands. And so it needs to know what commands it can run and what commands it has to delay. So it's not really practical for it to compute fully based on all of the possible information, which schedules are equivalent. What we want is a compromise, an easy way of knowing if two schedules, or if a schedule is serializable, with maybe the possibility that there are some schedules that might actually be serializable that we reject, where we might have a couple of false negatives, I guess. But we want to save some time. We want to use a model that's a bit simplified. So what we're going to do is define a basic set of rules that are sufficient conditions for schedules to be equivalent. So basically, if this set of rules can be used to turn this schedule into this one, then the two schedules are equivalent. Now, it could be that even if the rules don't, like even if applying the rules doesn't convert one into the other, they could still be equivalent. But we don't have the computational means to know that. So we're going to be defining a simplified set of conditions. In particular, we're going to define this idea of something called a conflict. And a conflict is a pair, so two operations that cannot be, whose order cannot be exchanged. So I'll give an example of a thing that is not a conflict. This operation here and this operation here. So I'll write them out in the order that they actually get executed. W2 of X and R1 of Y. Okay, so one transaction is writing to X, one transaction is reading from Y. These two things have nothing in common, these two operations. They are not in conflict. They do not modify the same piece of data. There isn't a read and write of the same piece of data. They're not from the same column of the diagram. And therefore, this ordering, W2R1, is in fact identical to this ordering, R1, W2. These two operations are not in conflict. Their order can be exchanged. On the other hand, let's take a look. This pair of operations, let's try this operation and this operation. W2 of X followed by, at some point in the future, W1 of X. Okay, so these two operations, currently the W2 happens before W1. And we know that they both modify the same value. And in general, we don't know what modification they're making. We have to assume that what this is writing is different than what this is writing to X. And that means that if this happens before this, the result in X could be different. And so the order of these two operations cannot be exchanged without changing the outcome of the schedule. And so these two operations are in conflict. So we're going to use that idea of looking at individual pairs and deciding, can I swap their order? And if I can, then I know that I can move them around in the schedule. If I can't, I have a conflict. And so basically what I care about is if I have two operations that do not conflict, so both transactions read X. Reading the same thing twice doesn't matter what order I do those two reads in. Just two reads in isolation, there's no way that a read modifies a value. So they can be swapped freely without modifying the outcome of the schedule. So here's how I will define a conflict. First, you send me a transaction full of operations. You're transaction 1. You read X, you read Y, you write X, R1 of X, R1 of Y. You write X, then you read Y again for some reason, and then you write Y. Okay, you send me this sequence of reads and writes. I have no idea what you're doing with X and Y. It's none of my business. And therefore, I don't know why you're doing it in this order, but I won't change the order of them. If you send me a list of operations for your transaction, so they're all from transaction number 1, then I will make sure that those operations stay in the order you sent them. I might move around other transactions things to be relative to you, but inside of a given transaction, the ordering of operations is always preserved. And therefore, two operations in the same transaction are always a conflict. And so even if they modify different, so read X, write Y in the same transaction. If you send me a read X before a write Y, I will always keep them in that order. And so to keep them in that order, I will mark them as a conflict. So in general, if you have two operations that affect the same transaction, so that's the subscript is the same, they are always a conflict. Okay, so that's one way of defining a conflict. The other two cases are if I have two writes by different transactions to the same piece of data, that's a conflict. If transaction 4 writes to X and then transaction 7 writes to X, I can't swap the order. If this is the order that they're already in, I have to leave them there. If transaction 7 wrote the value second, then the value that comes out of transaction 7 should be the value of X at this point here. So if I swap the order, that's no longer going to be the case. So two writes of the same value are always a conflict. And then any pair of a write and a read to the same value are a conflict. So two reads are fine. So R2 of X followed by R3 of X, that's the same as R3 of X followed by R2 of X. That's no big deal. But if I have R2 of X followed by W3 of X, well, then obviously, if I do this read after the write, I'm going to see a different value of X. So this situation is a conflict. W3 of X, in general, I have to assume if it comes before R2 of X, the result of this pair will be different than if it comes after. So to summarize, a conflict occurs in the three cases where you have two operations that are in the same transaction, because we're forcing them to be kept in order inside of a transaction, or two writes of the same piece of data, or a read and a write of the same piece of data. And so you can also view it like this. I like these conditions are a very, low-level way of viewing it. You can also view a conflict happens if you have between any two operations where both operations come from the same transaction, or both operations involve the same piece of data, and at least one of them is writing that piece of data. Any pair of operations that isn't a conflict can be swapped. And if you have a set of swaps that you can do inside of a schedule, so you start with a serial schedule and you perform a bunch of these swaps, the resulting schedule is called conflict equivalent. And we care about this. This set of rules is a great deal easier to enforce than the more complicated case of what is the final outcome in terms of numerical values. So if two schedules are conflict equivalent and one of them is a serial schedule, then there is a way of turning the other schedule into a serial schedule, which means it is serializable. You have to be very careful about this. I just said you can swap pairs of operations if they are not in conflict with each other. So what I meant was if you have R1 of X and then R2 of X, you're allowed to reorder them to be R2 of X followed by R1 of X. So pairs of operations. Intuitively, this should be applied to adjacent pairs, although the way I'm phrasing it here is that there could be all sorts of stuff between these two things and I could swap the two of them. So for example, if I notice that B and E here are not in conflict with each other, it doesn't necessarily mean that I can make this E and this B. So if B and E aren't in conflict, then both of these orderings are equivalent. If I just do B only and then I do E, then that's the same as just doing E and then doing B. But that doesn't mean that I can swap them inside of a big schedule. Because obviously, just because B and E don't conflict with each other doesn't mean that E doesn't conflict with D or something like that. So I should instead view the swapping that I'm doing as swapping of adjacent operations. So if I want to see if I can move E backwards, first I figure out, can I swap D and E? And then if I can, I've got E here and D here, then I figure out, can I swap E and C? And I try and move E backwards that way. I should not try and do a swap across multiple things because there could be conflicts that I jump over that I shouldn't be. Here's a schedule here. This is a non-serial schedule. So there's transaction 1, and there's more of transaction 1. There's transaction 2, and there's more of transaction 2. So the schedule I start with, S1, is not a serial schedule. But if I take a look at it, I would say, okay, so what can I do to this? First, R2 of x. Well, that's not in conflict with this because these are reads of a different value, which means this schedule is equivalent to R2 of x followed by R1 of y. And then I noticed that R2 of x and R1 of x don't conflict because they're both reads. Even though they're reading the same value, they're both reads. So that means that this is okay. That means that this is equivalent to R2 of x followed by R1 of x followed by R1 of y. I'm recreating my previous work to avoid having to erase it. So I can keep doing these swaps. And I'm going to see if I can, let's see if I can find something that I can't swap. So here, read y, write y. Okay, well, that's a conflict because they're both working on the same piece of data and at least one of them is a write operation. And then back to our original, can I change the order of R1 of x and R1 of y? And the answer is no. Because they both belong to the same transaction, they have to be kept in that order. But I am allowed to move R2 of x forwards by 2 positions, for example. So I could discover that it's actually equivalent to this. So I could do more of these swaps and I could say, okay, well, there's R2, there's some R1, there's R3, and then I have this. And then I can change the order of these two operations. These two operations are not in conflict. They're both writing, but they're two separate transactions on separate data items. And so I put W3 and then W2. It turns out I could keep going with this. So I could actually, instead of moving R2 of x backwards, I could move R2 of x, let's see. So R2 of x can go over here because it's not in conflict with R3 of x. R1 of y can actually go back here because R1 of y doesn't conflict with this or with this. And so what I could do is I could rearrange it so that I actually get R1, 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 then both of the R2s, and then R3 and W3, using these conflict-free swaps. And notice that when I'm done, the schedule that I have, S3, is a serial schedule. I've got all of T1, all of T2, all of T3. So using these conflict-free swaps, I was able to arrange operations into a serial schedule. If I can do that using only conflict-free swaps, I have what is called a conflict serializable schedule. So in this example, the schedule S1, because I could rearrange it to a serial schedule, that means that S1 is conflict serializable. S2 also is conflict serializable. So to be clear, a conflict serializable schedule can be rearranged to a serial schedule using only these conflict-free swaps. So it's conflict equivalent. That means that a conflict serializable schedule is a serializable schedule. Okay, that's great. But conflict serializability is a stronger condition. So we've seen before that there are some cases where a schedule is serializable due to a coincidence or something, and that schedule might not be conflict serializable. So there are cases where two operations actually do have a conflict, but where for some reason they don't actually interfere with each other in practice, and therefore if we swap them, nothing bad will happen. So we don't want to do that because we don't want to have to test the actual value of each operation. If we just use these rules, all we need to know is what operations are happening, write versus read, and what transaction do they come from. So there are serializable schedules that are not conflict serializable, but every conflict serializable schedule is a serializable schedule. Okay, so what about this one here? Is the schedule R1 of x, R2 of y, is that conflict equivalent to this schedule here? So the way I would answer this question in terms of is this conflict equivalent is, let's see if we can move operations around. Okay, so can I swap R1 and R2 here? So R2 of y goes down there. That shouldn't be a big deal. R1 of x goes down there. Those two things are not in conflict because they're both reads. The w just goes down unchanged. That's fine. R2 of x goes there. Okay, I'm allowed to do that because I'm allowed to move R3, swap R3 and R of y and R2 of x because they're both reads. So, okay, wait, W1 goes there. That shouldn't be a problem. We'll have to see what happens with R3. And then R3 goes there. So R3, we can see it crosses R2 and W1, both of X. So that read isn't affecting the same thing. So I can move that. And then R2 goes there and R3 goes there. And we can see at no point did I swap two elements that were in conflict. What about this one here? So so just to be clear, the answer is yes. It is conflict equivalent. What about this one here? We notice that R2 of x has to come first. So I'll draw where R2 of x goes. And then I have to ask the question, okay, am I allowed to have R2 of x jump over R1 of y? That's fine, both reads. And R1 of x, okay, again, both reads, different transaction. And then I've got W2 of y. Now that might be a bit of a tough one because, wait a minute. R1 of y and W2 of y both involve the same piece of data. And the way I've drawn it is I apparently want R1 of y to end up over here, which means I want to swap R1 of y and W2 of y, but they're in conflict, so I can't do that. So I'll draw an X. So the answer is no. And it turns out there might be other reasons for that. I only need to find one. So if the answer is no, that they are not conflict equivalent, all you have to do is find one case where you swap two elements with a conflict. If that's the case, then they are not conflict equivalent. It turns out that both of these two schedules over here are conflict equivalent. It turns out that they are not conflict serializable. It's actually interesting to note back on this slide here that this schedule, the one on the bottom, is the two S1 and S2 are not conflict equivalent, but the one on the bottom actually is conflict serializable. You can verify that yourself. We'll see in a minute that there are some easy ways to demonstrate whether something is conflict serializable, not to actually ask if two arbitrary schedules are equivalent, just to ask, here's one schedule by itself, is it conflict serializable? We're going to get to that in just a minute. It turns out, though, that schedule S2 is actually conflict serializable because you can turn it into this thing. So that means this comes down here, this comes down here, and then that's the end of transaction 2. R1 stays there, R1 stays there, and then we move R1 of y back and R3 of x forward, and then we get a serial schedule, so it's conflict serializable. So here's the question. I mean, we know that we can do these conflict-free swaps, and it's one thing to ask the question, are these two schedules equivalent? But it does seem a bit nightmarish if you don't know, if you don't actually have two schedules. If I just say, here's one schedule, yes or no, is this conflict serializable? Well, do I just try all the different ways of, can I swap R1 all the way back here? Maybe I can't. If I can't do that, can I swap R2 and W2 all the way forward? There are 6 different serial schedules for 3 transactions. Do I want to try all of them? So we could, I guess, just take every possible serial schedule and see if our schedule S is equivalent to it with conflict-free swaps. But that sounds disgusting. I don't want to have to do that, especially if there's like 10 transactions. So what else can I do? Well, this is a typical algorithm problem of, we've got this, our problem is getting more and more complicated, our input is getting larger and larger, and it's becoming a bit of a headache. If only there was some algorithm or data structure device for some previous course that we know from previous experience always makes our life easier for problems like this. Well, it turns out that there is. And it's great when we get to this part of the course. Some of you actually took 225 with me, and there were some moments in 225 when I would say, here's a weird way that we use graphs for something. And none of you believe that it's important now, but there will come a day when you really, really wish that you'd paid more attention here. And this is one of those days. And the next lecture will contain a big one of those. But it turns out that there is something we can draw called a precedence graph. That we can use to map out conflict relationships between transactions. So what we do is, if we have several transactions, I'm just going to mock up a couple of transactions here. R1 of x, R2 of x, and then R1 of y, and then W2 of y. All right, so I've got 2 transactions. Actually, I better do one more transaction. Let's do W3. Oh, we'll do R3 of y. Okay, so I have 3 transactions here, and they are called T1, T2, T2, and T3. And what I do to create a precedence graph is I make a graph with one vertex per transaction. So not per operation, per transaction. And then I add, so it's a directed graph. So every edge that I add will have a direction. It'll be an arrow pointing in one direction. And I add an edge for every pair of operations. And to be clear, it doesn't have to be just an adjacent pair. It could be a pair of operations that's distributed across, halfway across the schedule. Every pair of operations that meets these rules, I add an edge. And so the rules are, I have two operations in the pair, and one of them involves, the two operations involve different transactions. And I add an edge from the first transaction to the second one if that pair of operations is a conflict. So I'll map that out here. So R1 of X, R2 of X. Okay, not a conflict, so it doesn't meet this criteria, so I ignore it. Okay, R1 of X, R1 of Y. Okay, well, they don't involve separate transactions. Okay, so I ignore it, I keep going. R2 of X and W2 of Y. Okay, they don't read the same, they don't work with the same data item, not a conflict. Okay, R1 of Y, W2 of Y. Okay, so that's a conflict. They both work with the same piece of data, and one of them is a write. So what it says here is TI is R1. So the transaction that comes first is the is the source of the edge, and I draw an edge from transaction 1 to transaction 2. Okay, so there's the conflict. Okay, so then I've got oh, wow. Okay, so then I've got this. So T1 goes to T2, and then I look at the conflict. Okay, what about R2 of X, W2 of Y? Nope, don't care. Let's see. W2 of Y, R3 of Y. Okay, that is a conflict. So I draw an edge from transaction 2 to transaction 3. Whatever transaction comes first in the conflict is the transaction that is the source of the edge. Okay, and then what about R1 of Y, R3 of Y? Well, that in and of itself doesn't look a lot like a conflict to me, so I think that's all we need. So I have this. This graph is my precedence graph here. And we might notice that there are certain properties, if we look at that, we say, wow, T1 points to T2. Maybe that means T1 has to come first. Interesting. So we'll revisit that in a couple of slides. But we can use this graph and some 225 stuff to easily decide, even given a complicated schedule, whether that schedule is conflict serializable. Now, the reason that we're using a graph here is not just because I love graphs, although I do love graphs. It's because it turns out that directed acyclic graphs, which are a way of representing this, which might show up in like Math 222 or something, that's a really useful modeling technique for scheduling. If you've ever used a piece of software like a build system or like Make or whatever, it uses directed acyclic graphs and this. And you all thought you'd never need to know this again. Topological sorting. It turns out that directed acyclic graphs and topological sorting is a great mechanism for handling scheduling problems. And that's what this is, a conflict serializable schedule. And so the goal of the precedence graph is to find some way of deciding if something is conflict serializable, and then ideally, if it is, figuring out what serial schedule it's equivalent to. And it turns out that if you develop the precedence graph, the schedule you started with is conflict serializable if and only if the graph you have is acyclic, if it's a directed acyclic graph. So that means it has no directed cycle. And just for review, here is an example of a directed cycle. Right? So I can follow the arrows to get from one place back to itself, following at least one edge. This, however, is not a directed cycle. It's certainly true that these three edges form something that might look like a cycle, but notice that I can't go all the way around the cycle following the direction of the arrows. So this is not a directed cycle because the cycle isn't with respect to the directions of the arrows. So if I just create the precedence graph for the schedule is conflict serializable if and only if the graph has no directed cycle. And then it turns out if the graph is acyclic, if it has no directed cycle, you can get a serial schedule by performing topological sorting on the vertices. And I will get to that. We will do the minimal amount of review of this. You have to, unfortunately, we don't have time to go to much more detail about it, but we will talk about it. In some of the in-person tutorials, I'll talk about it further. So here we have this schedule here. Now notice that no matter how long the schedule is, the number of vertices in the graph is just the number of transactions. So if I have 3 transactions that each have 10 million operations, I'm still going to have a 3-vertex precedence graph. Okay, so I have this precedence graph here, and the first question is this schedule conflict serializable? And it's conflict serializable if there is any directed cycle. It doesn't matter how long it is. And in this case, I notice if I start at T1 and I walk over to T2 and then I walk back to T1, that's a cycle. And so it doesn't even, I was hoping it would label the cycle. There's the cycle. Because it contains a cycle, it's not conflict serializable. Okay, now I've got this schedule. And the graph above is the precedence graph for this. Okay, so let's see. If I go looking for a cycle, I can go from T1 to T2, and then I'm stuck. Okay, I can go from T1 to T3, and then I'm stuck. And you might be able to see there is something that resembles a cycle, but there is no directed cycle in this graph. And therefore, this is conflict serializable. Actually, I'll back that up to avoid spoiling the punchline. So it is conflict serializable because there is no directed cycle. Okay, the next question is, what is the serial schedule? Now, remember that in a serial schedule, we'll have something like R1, W1, R1, R1, W1, R2, W2, W3, 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 R3. Like, we'll have all of the stuff for T2, all the stuff for T1. So if you notice an edit there, that was the my PDF reader crashing, which is rude. But quite helpfully, when it came back, it kept the drawing I'd made. So I was I was on a roll there. This throws everything off. As I was saying, when you have a serial schedule, what you end up with is every operation for each transaction in a row. So there's T1, there's T2, and then there's T3. So if I want a serial schedule, I don't even care about the order of these because we know what order they're in. Everything in a transaction is kept in order. We just care which transaction comes first, which transaction comes second, which transaction comes third. And if you know that, if you know that T1 comes before T2, comes before T3, you can always reconstruct the actual serial schedule by just writing out all the so I'll do it here, writing out all the operations for T1, then all the operations for T2. Now, okay, how do we use that for our purposes here? So I have this precedence graph, and I hate this because it cut out just as I was about to talk about topological sorting. We have this precedence graph. We know that the schedule is conflict serializable, and now the question is, what is a serial schedule? And so once we know it's conflict serializable, we can compute a serial schedule by performing topological sorting. Now, what is topological sorting on a directed graph? Well, go take a look at your 225. But you might have spent a lot of time on it in 225. It turns out that for the purposes we need it here, we don't need to write an algorithm to do it. We just need to be able to analyze these schedules on paper. So here is my brief review of topological sorting for the sake of answering exam questions or assignment questions and reasoning about databases. You have a graph. It's a directed acyclic graph, which means there has to be at least one vertex. There could be more than one. There has to be at least one vertex with no incoming edges. So in this case, T2 and T3 both have incoming edges. So to perform topological sorting, at each step, pick a vertex with no incoming edges. In this case, it's T1. I'm going to add that to my topologically sorted list. Okay, there's T1. I add it to my list, and then I delete T1. I just completely get rid of it from the graph. I delete it and all of its edges. They are gone. If I had a board, I would erase them, but I do not. And I don't want to try erasing the lines in the PDF because I've already upset my PDF reader enough for today. So I deleted T1, and then I just keep repeating that process. I choose a vertex with no incoming edges. There could be multiple choices. I just take any of them. In this case, there's only one choice. It's T2. So I choose T2. And then I delete T2 and all of its edges from the graph. Okay, and then I choose the vertex with no incoming edges. It's T3, and then I delete T3. Now, this is my serial schedule of transactions. And so now I will write that down here. So let's see, R1 of X, R1 of Y, R1 of Y again. Is that all for R1? Yep. Okay, so there's T1 taken care of, and then I've got R2 of X and W2 of y. And then I think I just have, maybe it's good to cross these out as we go through them. So R2, R2, and then I've got R3 of x and W3 of x. So there's my serial schedule. Now it says that here. It just doesn't feel the same if I don't do the topological sorting myself on the slide. Okay, so here's a graph that is the precedence graph for this schedule here, which has 4 transactions and several pieces of data. You might notice that the number of, as I said before the PDF reader died, the number of vertices is just the number of transactions. So the number of pieces of data doesn't really have much of a bearing on the way the graph looks. You'll notice in this case, this is not conflict serializable. There is a huge cycle here. If I just walk across every single vertex, I can get back to vertex 1. So it isn't conflict serializable. But also notice that it isn't obvious from just looking at 2 transactions. The reason we need a precedence graph is because the conflicts that produce the lack of conflict serializability, the problem that's caused here is very global. It's not just a problem with T1 and T2 or T2 and T3. It's all 4 transactions together. What that actually is saying is that if I delete a transaction, so if this schedule didn't have T4, then the graph would just be like this. It would be conflict serializable. So that's one reason why you need to draw a precedence graph. And you know how much I like graphs, so I'll find a way of making sure that you draw one on the exam. One of the assignment questions also involves a graph, so it's good to brush up on graph stuff. So the key to note here is that it's not conflict serializable, but that the cycle is a result of, it's not just one pair of transactions, it's all the transactions working together that have created the problem. So without looking at it with a graph, or just good luck, I guess, it may not be possible to actually see this issue. Drawing the graph, I think, makes it obvious. Once I have this graph, I'm done. I just say not conflict serializable. End of story. There's no need for fiddling around. Trying to fiddle with individual operations can be error prone. Okay, so we've got to this point now. We've seen that, first off, if you give me a schedule, I can check whether it's conflict serializable. And that's great, I guess, but that's for analysis. I mean, what does the database actually do? The database doesn't get this listing. We don't hand the database this weird arbitrary listing of reads and writes. The database gets one operation at a time. Transaction 1 sends a write. Transaction 2 sends a read. The database doesn't know what transaction 1 is going to do at the end because transaction 1 isn't done at the beginning. And actually, even worse, transaction 1 might not even know what it's going to do later. Maybe based on the result, let's look at transaction 2, I guess. Based on what comes back from this read, transaction 2 might choose to do a write or not. The database doesn't know what the transactions are going to do, so this modeling is useful for talking about serializability, and just to be clear, it's on the exam, but the modeling isn't what the database does internally. The database doesn't have that amount of information. What it gets is a set of commands one by one for each transaction, and it has to decide whether to run them, whether to abort the transaction, or whether to delay them. And so we're talking about the action of a DBMS scheduler. And it has to, I guess, usually resort to delaying a transaction if it can't be run right now. And this is where we can finally begin to talk about when to lock pieces of data. So one obvious way of preventing concurrency problems is locking. If we know that there are 2 operations that are in conflict, 2, let's say, writes to the same piece of operation, we can allow different things to run at the same time, but then use a mechanism called locking to prevent certain resources from being used twice by different users. And that means that if you have 2 operations that are trying to run at the same time, so 2 transactions try to write to the same piece of data, one of them gets delayed, because only one transaction can have the lock at a given time. Once a transaction has locked a piece of data, nobody else can touch that data until after the transaction has unlocked it. So using locks, we can avoid the problems we had earlier, like one transaction having a stale value for a piece of data, because the transaction can lock that piece of data so nobody else can use it or modify it in the meantime. So we're going to add to our menu of different operations, we're going to add lock and unlock. In the model we're going to use, Once T1 has locked the data item X, T2 is not allowed to lock the data item X. Any attempt T2 makes to lock X will not be serviced until after X has been unlocked. And additionally, nobody is allowed to read or write any piece of data unless they hold the lock. In other words, you can't run a read X or write X unless it occurs between a lock X and unlock X command. And if you try and lock a piece of data that somebody else has already locked, then you're not allowed to do it. Now, the way this would actually work is probably T2 wants, clearly the next thing T2 does after locking Y is locking X. That's obviously what it wants to do. So why is it wait until down here? Probably what happened was T2 locked Y, and then it asked the database to please lock X. And the database said, I'm sorry, I just let T1 lock X. You're going to have to wait. And so this command is just held in the queue until finally down here, the database can get back to T2 and say, okay, here's the lock. So T2 just gets delayed for 4 steps. So I'm going to keep drawing it as this blank space, but we can assume that that gap might be the result of T2 just taking a while, but it could also be the database deliberately delaying the lock that T2 asked for, and that actually the lock it was asking for it earlier, but it didn't get it until time step 6. So locks are a good way of creating atomicity. I mean, because only one process can hold, only one transaction can hold a particular lock at a time, everything that happens between lock and unlock is atomic with respect to the value of X. Nobody can see what happens to X here or here. Anybody that wants to look at X has to wait until it's been unlocked. And that means that nobody will be able to see the internal operations happening between lock and unlock. X has a value here, and then X has a value here. Everything that happens in between is one atomic operation. Here, these are both feasible schedules of these two transactions. This is a purely serial schedule. You'll notice that all the interesting stuff is still happening in a sort of serial-like order. Here's where T2 is doing its work. Oh, let's clear this. Here's where T2 is doing its work, and here's where T1 is doing its work. And they're all happening in a group together because of the way the locking has occurred. And this schedule is also feasible. So in this case, T1 wanted to lock X, but T2 got there first. So T1 has to wait until T2 unlocks X. But then T1 jumps right in and locks X. And then T2 doesn't get around to unlocking Y until after T1 is finished. That's fine. So nobody can lock X until X has been unlocked. But there's no reason why we have to have the unlock Y happen immediately after the unlock X. So we'll do the same thing we did before. We'll use this condensed notation. So L and U now mean lock and unlock. So here are the rules we're going to impose on locking. Nobody is allowed to use a resource until they have the lock. So what does it mean to have the lock? Well, if you're transaction 1, you send an L request. So you would send L1 of X to the database. The database will either give you the lock now, or it'll just sit and wait a minute. It'll delay for some period of time. We call this blocking. So you ask for the lock, the database might take a while to get back to you, and then it will give you the lock. There are some cases where database systems can have it defined where if it can't give you the lock within, let's say, 10 seconds, it'll just abort your transaction. It'll say, sorry, extenuating circumstances, your transaction can't be serviced, and then abort the transaction. That is to avoid an issue called starvation, which we'll touch on in a minute. But for now, we'll assume the scheduler either gives you the lock or it blocks you, and so you have to wait until the lock can be granted. The key here is that if you ask for a lock, then you have to wait for that request to finish. If you ask and the lock isn't available, you still have to wait until the lock is available before continuing. You can't do anything else until you have the lock. You also have to, of course, have the lock before you're allowed to do any operations on the data that the lock refers to. So if you need to use X, you are not allowed to do any read or write of X until you have the lock, which means in this case, L1 of X is done. So again, our interpretation of L1 of X is you request the lock, some amount of time passes, and then you have it. Under no circumstances will you get to item numbers to the R1 of X without having the lock. If the database can't ever give you the lock, the whole transaction gets aborted. So there will never be a case where you don't have the lock when you do that read. And then when you're done, all your operations, you send a U request to release the lock. And then another transaction can scoop up the lock as soon as you're done. So locking actually allows you to achieve real concurrency, not just interleaved operations. You can actually now have two transactions that are time step 1 actually has two things happening. Two independent things are happening in time step 1. In time step 3, one transaction's writing an item, one transaction's reading a different item. That's fine, because we know that each transaction owns the items that it's working with. As of step 3, nobody can touch Y but T2, because T2 has the lock on Y. And as of step 2, nobody can touch X but T1. And so it's fine, because we know that at each step, anybody modifying or using a piece of data will have locked it. It is now fine to actually allow two transactions to execute actually concurrently. Now, of course, as I said at the very beginning of this odyssey, although this is now allowed, we can still model it like this. There's really nothing, there's no problem with modeling it like this. Anything that can be done concurrently, we can, I guess, modulate and turn it into a linear schedule. And as a result, although this is possible and valid, we can continue modeling it as if it is a linear sequence. Now, the problem here is that locking by itself doesn't guarantee conflict serializability if we're not careful. So here's an example of two transactions where T1 uses X and then unlocks it. And then as soon as it unlocks it, T2 jumps in and does a bunch of stuff. And you might notice that T1 can't do anything after this point because T2 has a lock on Y. And then T1 needs a lock on Y, so it has to wait. And if you were to take a look at these, there are conflicts that exist here. So this and this, these two things are in conflict. This and this, these two things are in conflict. So if this were modeled as a linear schedule, this is not conflict serializable because there's no way I can ever move T2 to be before T1, and there's no way I can ever move T2 to be after T1. So it's not conflict serializable even though I'm using locking. And the issue basically is that T1 needs both X and Y, but it doesn't need them at once. And what it's currently doing seems like, being more considerate, I guess. It only locks X, but then it finishes with X. Now it has no locks. And then it has to sit and wait for a lock to appear for Y. In the meantime, somebody else swoops in and does a bunch of work, and we get this non-serializable result. So what we have to do is be a bit more selfish. We can use something called two-phase locking. So two-phase locking is saying, I'm going to need to read a bunch of books. I'm going to just take them all out of the library at once. I don't want to take out one book from the library and then have to wait 6 months when I take it back because somebody got the next book. I'm just going to take out all the books at once. So two-phase locking says, basically, if a transaction needs a bunch of locks over its lifespan, so a transaction does 10 million operations, and over those 10 million operations, it needs to lock 5 different things. Two-phase locking says that every single lock request must appear before there are any unlock requests of any kind. Now, it's not saying you have to put all of your locks at the beginning and all of your unlocks at the end. It is saying, however, that you aren't allowed to unlock anything until you've locked everything you will ever need. So there will be always a moment in time, right before your first unlock request, where your transaction holds the lock to every single data item it needs. So here's an example of two-phase locking being used here. Notice I lock X. I don't lock Y immediately. Two-phase locking isn't saying necessarily that I guess the library book example was not nuanced enough. I don't have to take out all the books at once, but I don't return any books until I have all the books that I'm going to need. So here I lock X, then I work with X, and then I lock Y, and then I work with Y. Notice that as soon as I've locked X, T2 can't do anything. T2 has to wait for X to be locked. Even though T2, might later need Y, T2 can't start until it has its lock on X. So T1 now has free run over X, then it locks Y. And then it works with Y, and then it unlocks both of them. And once it's unlocked both of them, it's now done, and T2 can swoop in and lock all of its data and work with it. And it turns out that when you do it this way, what you end up with is sort of a natural serialization happening of transactions, where if two transactions need the same piece of data, then whoever sends the lock request first gets to go first. Because once T1 has locked something, everything else in T1 happens, well, up to the unlock statement, before T2 can do anything. And so as a result, it sort of ends up blocking things back together in a pretty serial looking form, but it only is serial between transactions that conflict. So just to be clear, I know that, after all this time, we're down at, after 90 slides, after spending all this time saying, yeah, serial schedules are not great, we need to allow we need to achieve isolation so we can allow real concurrency, and then saying, no, we've got this two-phase locking that basically gives us back serial transactions, but with an hour and a half of extra work in the middle. So keep in mind that I am still allowed to have interleaved transactions. I just have to make sure that they use separate pieces of data. So here, T2 locks X, then T3 locks Y. And then they work independently because they don't need the same piece of data. Great. And then T1 at the very end needs both. So T1 has to wait. And so we do get some fully serial transactions if they need data that other transactions need. But we are still achieving conflict serializable interleaved transactions. And just because we're using two-phase locking doesn't mean we have to do all our locking at the beginning. So here, T2 uses X, locks and unlocks X, and T1 can't start until T2 is done. So here's T1, it locks X. T3 only needs Y. And notice that T1, it's not allowed to unlock anything until it's locked everything. But it's not required to lock everything at the beginning. So it doesn't lock Y until it first needs it. And that means in the meantime, T3 can jump in and begin working with Y. And then T3 finishes. And of course, T1 has to wait for T3 to finish before it's allowed to go here and lock Y. But T1 and T3 can still be interleaved. There's nothing wrong with this. It's true that if you have a transaction that needs tons and tons of locks, it might wait a while before it gets them. And maybe there'll be this serial section of the schedule where only one transaction can run. But there's no reason that two-phase locking inherently results in fully serial schedules. And of course, what tends to happen is in a database, you have lots of transactions that are working with pretty much disjoint data, maybe different tables, maybe different rows in the same table. But as a result, it's pretty likely that you'll get transactions that can run pretty much concurrently. So here, for example, we have T1 and T2 are fully independent. So this needs A and B, this needs C and D. So they run basically identically concurrently. And then T3 needs E and A. So it locks E and then waits, and then it gets A down here when T1 is done. T4 needs F and B, so also things that T1 has. So it locks F, and then it's able to grab B just after T1 unlocks it. And then T4 and T3 are independent. So we're still achieving pretty good concurrency here, and we have to compromise in cases where two transactions need to modify the same piece of data. Now, it turns out that we have to do locking even if we're just reading a piece of data. So here, T1 locks A and unlocks A because it has to read A, because we want to avoid cases where A has inconsistent values. We'll see in a minute there's a locking strategy we can use where if a bunch of transactions want to read the same value, they can all share the lock. There's no need for them to each take their turn with the value. But we never want one transaction writing a value while other transactions can read that value. So basically, we finally reached a point where we can say, if we use the two-phase locking, so you have all the locks before you relinquish any of them, then any any schedule that respects those constraints, which means you do lock stuff before you use the resources, and of course you obey two-phase locking, any schedule with that is conflict serializable. So you still have to know how to tell me whether a schedule is conflict serializable, but if we use two-phase locking, we finally have a remedy to this problem. Now, two-phase locking guarantees conflict serializability, but we've been saying all this time that there are some transactions that were destined to fail. And as a result, we don't worry too much about what happens if transactions run into an impossible situation. There is an impossible situation that can result as a direct result of locking mechanisms. And it's where two transactions fight with each other infinitely. So back here, we had transaction 3, for example. It's not fighting with T1, it's having to wait its turn. It can't get the lock on A until T1 is done. But there are cases where two transactions can become interlocked such that both of them want something the other one has, and neither of them will give it up. That's a tough one. And unfortunately, we could just say that if transactions do that, they should fail. But we may want to find a way around that. And keeping in mind, if a transaction fails, you could always send it in again. I mean, if the database terminates your transaction because it says, sorry, your transaction timed out because it couldn't get a lock, you're welcome to send it in again. You might even notice in some of our automation that we use, we have had cases where, I guess we wouldn't have had it on a select statement. There are cases where we run operations more than once because we acknowledge that they may actually fail in some cases due to locking not working. So what about this? This schedule here is serializable, obviously, because it's, a serial schedule. And so transaction 1 locks X, reads X, and then writes a value to Y. Transaction 2 reads Y and then writes a value to X. And because of this, these are both obeying two-phase locking. Because of this, transaction 2 locks Y, then X. Transaction 1 locks X, then Y. Because it doesn't need to lock on Y until after it's done reading X, and T2 vice versa. So what about this? This is the same list of operations. So this is conflict serializable. Okay, T1 locks X and then reads it. In the meantime, T2 locks Y and then reads it. So then T1 says, I want to lock Y. And the database quite predictably says, you're just going to have to wait a minute. T2 has Y locked. T2 says, I want to lock X. And the database says, you're just going to have to wait a minute. T1 has a lock on X. And then T1 sits there and waits. And then T2 sits there and waits. And then T1 just is still waiting and T2 is still waiting, and neither of them can ever finish. Because T1 is waiting for T2 to finish, but T2 can't continue until T1 finishes, and T1 relinquishes its lock. What we have is what's called deadlock. Neither transaction can continue because both transactions are waiting for the other one. And so they'll both wait forever, and neither will ever make any progress. And likely what will happen is the database will notice after some period of time has elapsed that these transactions have gone stale and terminate them. This is a bit of a rough one. This is where concurrency with a capital C comes into this course. And for some reason, maybe it's because I've been giving this lecture for like an hour and a half or something. Suddenly I'm feeling all hungry and philosophical or whatever. I don't know if that's a problem for 370 though. It turns out that preventing deadlocks is a thing. When I say it's a thing, it's the kind of thing you might want to spend 3 weeks on. And we're out of patience for 3-week-long topics in this course, but if you want to learn about deadlock, you can always take CSD 360. It covers, there's all sorts of schemes we can use here. The basic one would be the database just saying to T1 and T2, if you don't finish within the next 10 minutes, I'm just going to terminate you and you're going to have to start again. And hoping that when they start over again, they don't end up deadlocked. That's one option. I don't want it, we won't teach 360 and 370. What we can do here is add one more locking condition, which is, it turns out if we look at this issue here, what was actually happening is T1 locks X and then Y. T2 locks Y and then X. And as a result, they end up sort of meshed together in an unfavorable way. So we actually can remedy that by imposing an ordering on locking. This isn't the best, like two-phase locking can have some performance disadvantages. There are reasons why we should allow locking to happen in different orders. The problem is, obviously, deadlock is a terrible situation. Deadlock is a very difficult situation to remedy. And so either we use a really complicated remedy or we use a simpler remedy that has other consequences. And the remedy we use here is if we force every transaction that locks resources to lock them in some predefined order. So one example would be we've got data items X, Y, and Z. And if you lock multiple data items, you are required to request the locks in alphabetical order. So if you lock both X and Y, you must lock X first. If you try and lock X, okay, try that again. If you try and lock X and you already have the lock to Y, your transaction is aborted because you're supposed to take your locks in alphabetical order. If we do that, it turns out that the problem that we just saw is avoided. So deadlock won't occur in that case. So in this case, T2 and T1 both lock X first. And that means that if T1 if T1 gets the lock first, T2 has to wait until T1 is done. There's no way that T2 will pick up something that T1 wants unless T2 doesn't need that thing. Unless T2 doesn't need anything that T1 already has, in which case there will be no deadlock. This will prevent all deadlocks at the expense of sacrificing some freedom in what order things happen. It isn't the best remedy for a database system because how do you necessarily know when you're asking for a particular row of a particular table? How do you know what its ordering is? Like when to lock it relative to other rows. You have to define some universal ordering of all the data items in your system if you want to do that, which isn't really practical. So that is a remedy that I think for our purposes we can just sort of leave that there. There are ways of programmatically preventing deadlock. There are also other sort of heuristic approaches, like if two transactions end up stalling indefinitely because they appear to be waiting for locks, terminate one of them and unlock all of its data, and then tell that transaction to start again. So rerun the same transaction. That's not great, but we know that transactions can sometimes fail. And it's not our favorite, but it's something we may have to do sometimes. I'm going to leave the subject of deadlock there and just put in a plug for go take CSC 360 if you want to talk about more ways of resolving deadlock. I want to talk a little bit more about some ways of loosening up locking conditions. So here are three transactions where one of them writes and the other two just read. And we might notice that if T1 and T2 only ever read the value of y, they're never going to conflict with each other. R1 of y and R2 of y aren't conflicts. But under our current locking regime, we have to lock y before we can use it. So T1 locks y and T2 has to wait. Not only does T2 have to wait, but locking and unlocking aren't trivial. They do require resources on the database side. And there's communication overhead and whatever. So we would rather not lock and unlock if we can avoid it. And we'll notice that certainly T3 needs a lock on y, because nobody should be allowed to see y here or here while T3 is working with it. But T1 and T2 don't, because T1 and T2 just read. On the other hand, if T1 and T2 don't lock y, there's a chance some other transaction could jump in and begin writing to y in the middle. So we still need T1 and T2 to be protected, but not from each other. If what I mean by my last point there is if I just don't lock y for T2, if I say, wait, I'm just reading y, why do I bother locking it? If I get rid of the requirement to lock, I might end up with this situation happening. Because I don't lock y, this operation can happen wherever I want it to, which means it could happen in a funny, inconsistent location. So I need some protection on T2. I need to make sure T2 doesn't get in the way of other transactions. I just don't mind if this read and this read happen at the same time. So what we can do is remedy that by having two different kinds of locks. We can call a shared lock a special type of lock that more than one transaction can hold at a time. And an exclusive lock is one similar to what we already have. So an exclusive lock is a lock that nobody else can hold, and we use an exclusive lock for writing to a value. If you want an exclusive lock, you have to wait until all of the shared locks have been unlocked. If you want a shared lock, you have to wait for any exclusive lock to be unlocked. But if there are already shared locks on a resource, you are allowed to also have a shared lock on the resource. That's why it's shared. If you want to read from a resource, you must have a shared lock on that resource. And you can only acquire a shared lock if there are no exclusive locks. But it's fine if there are already shared locks. You can take out another shared lock. If you want to write to a resource, you must have an exclusive lock. You can only get an exclusive lock if there are no locks, whether they're exclusive or shared. No locks of any kind can exist. And if there are any, you have to wait for those to be unlocked before you can have your exclusive lock. If we do this, we end up with this situation. So I take out a shared lock on y in T1, and then in T2 I do the same thing if I want to read y, and then I unlock it when I'm done. I take out an exclusive lock on y in T3 because I'm going to want to write. I'm not allowed to write unless I have an exclusive lock. If I do that, because when you have a shared lock, you're allowed to take out other shared locks on the same resource, normal locking would dictate, if you just had a regular L here, a normal lock would say that if T1 has the lock, you don't get a lock until T1 is done. With shared locking, if somebody else has a shared lock and you also want a shared lock, that's fine. You're allowed to take out a second shared lock, which means you can read and T1 can read and they can be interleaved. On the other hand, T3, which wants an exclusive lock, has to wait until there are no other locks on the resource. That means it has to wait until after T1 has already unlocked its shared lock. And so this also applies if I want to do full concurrency. We could actually have T1 and T2 operating fully in parallel, where this pair of operations, this pair of operations, and this pair of operations, all those pairs happen at exactly the same time. Whereas for T3, because of the exclusive locking, we'd have to wait all the way until those locks are returned. Okay, so we're finally at the end here. So serializability, the idea that a transaction is fully serializable or conflict serializable, is the gold standard. I would like, in general, to have the option when I start a transaction that from the point of view of that transaction, nothing else is happening at the same time. It has the database to itself. It has full isolation. The problem with that in practice is that that's a pretty high standard to meet. I mean, I have to lock all the resources and whatever. That's a tough one because I might have millions of transactions happening, and maybe I don't mind if a little bit of inconsistency creeps in. Not inconsistency in terms of the constraints, but maybe I don't mind. Let's scroll way up here. Let's hope the system doesn't crash again. Maybe I don't mind if my transaction gets the wrong idea about some value of X in the middle. Maybe I don't mind. So I want the ability in SQL to maybe waive those requirements. So I need in SQL, in any ACID compliant database, I need the ability to have full isolation. But SQL does define levels of isolation that are lower than serializability, which allow some transactions for less important things to run even if full isolation can't be observed. And a typical case I might want that is, suppose I'm running I have a database for all the bookings of flights. Anybody who wants to book a flight should do so in a fully isolated, serializable transaction, because the booking of a flight is a big deal. I want to make sure all consistency is maintained. On the other hand, maybe at regular intervals, I generate reports of how full every flight is. So I just generate a quick readout of how full all the flights are. I do that every 5 minutes or something. Or I do that every 10 seconds. That report isn't used for anything besides basic, I just glance over it. I'm just administering the system. I just look at the report for statistical reasons. I don't mind if that report has an error every now and then. But more importantly, I don't want to have to lock a bunch of data just to generate that report. Because, thousands of flight bookings come in every second. Maybe if I generate that report, I don't mind if I don't get full isolation. So the key here is that if I set an isolation level for a transaction, that applies to the way other transactions influence my transaction. So if you start a transaction that's serializable, no other transaction can interfere with you. So just because my transaction has a different isolation level doesn't give me the right to interfere with you. But I am allowed to say whether other transactions can interfere with me if it improves performance. And you can do this as part of the start transaction or in a set command after the transaction is started. And there are 4 levels. They are serializable, which is what we've just spent an hour and a half talking about. So that's the gold standard. And then there are these 3 other ones. Now, the SQL, I think quite reasonably, the standard says, look, because we want full isolation, this should be the default. Every transaction you start should be automatically in serializable mode unless you say otherwise. As we're used to by now, nobody apparently who implements database systems reads the standard, and so it turns out that most DBMSs do not actually enforce this. If you want serializable, you have to ask for it. By default, transactions start in a different level. In Postgres, it's this one. So I'm going to go through what the levels mean. So SQL just gets no respect. In all these other courses, we can talk about the rules being followed. We know that a C compiler requires certain things in terms of syntax, and yet SQL has this massive standard, and all these database systems basically ignore most of it. So let's talk about the options. Okay, so first, a transaction in serializable mode gives us the behavior we've just spent an hour and a half on, which is from the point of view, if I am a transaction T in the serializable isolation level, then from my point of view, from the point of view of T, every other transaction either finishes before me or starts after me. And we know already that that means I'm conflict serializable. Other transactions can be happening at the same time, but as far as I can tell, they either have to have already finished or not started yet. If I use the level called repeatable read, that means that if I read anything in my transaction, and I read the same thing again later, then that read has to give me the same value. Because obviously, if my transaction believes it's running in a vacuum, and I read the value of y and it gives me the value 6, and then I wait a minute and read it again, of course I expect it to still be the value 6. I don't want, it to change in the middle if I haven't done anything to it. So if you're in repeatable read mode, the database has to do whatever is necessary to make sure that once you have read a particular value of a piece of data, that any future read that you do of that value will return the same value. It's not saying that you're not allowed to modify a particular value while the transaction is running, but if that transaction has read the value must be the same next time the transaction reads it. So that's there's a bit of nuance to that. Maybe I can duplicate that here. The diagram doesn't give me many options. How about this? Okay, so after T1 is started, T2 modifies Y. In a serializable case, that might be, actually even in serializable, that wouldn't be a big deal, just because that is conflict serializable. But here, Y does change after the transaction 1 is started. But transaction 1 then reads Y. As soon as it reads Y, the clock starts ticking. After it reads Y, every future read that it does of Y must have the same value. And there are a few ways that can be enforced. Okay, I guess I just didn't trust my slides. So this schedule isn't serializable. There's a conflict in there. I guess it would be this W and this R are a conflict on one end, and this W and this R are a conflict. So yeah, this is not serializable because you can't put one before the other. And it does meet the criteria for repeatable reads, though, because once I've read Y in T1, T2 is not allowed to modify Y. Any attempt T2 makes to modify Y, so it tries to modify Y here, this gets delayed until after T1 is done. Now, database systems have a few options here. They could prevent any writing to Y after you've read Y, or they could just make a snapshot of Y and then give you back a phony value of Y every time you ask for it, and let other people modify Y on the side. That's also allowed. That's an implementation thing you'd hear about in an advanced databases course. I think we call that CSC 502. It's got a 4th year number too. It's offered next spring. You can take it. The next level below repeatable read is called read committed. So read committed says if you are transaction T2 here, you can read a value multiple times, and I won't guarantee that every time you read it, you'll get the same value. That's what repeatable read guarantees. You can read a value like X multiple times, and maybe its value will change. But I guarantee you that any value you see when you read X will be a value that was put there by a transaction that has already committed. So to be clear, another transaction that modifies X while you're using it, you would never see the value of X that it put there unless that transaction did commit. And the reason that's significant is, what if the transaction rolls back? You don't want to see data that's the result of a transaction that hasn't committed yet. Because what if the transaction doesn't commit? What if the data you see ends up never having existed because the transaction has to abort and roll back? So that's why read committed is important. Read committed says, yes, it's true if your transaction is long, the data you read might change over time. But I guarantee you that at any given moment, when you read something, that data is really in the database. It was put there by a transaction that did succeed and has committed. So it's really there. That's read committed. So yeah, in this schedule here, when I get to this situation, I would be violating repeatable read normally. So here, T1 modifies X after if I'm T2. If I'm T2, I look at X, and then somebody else modifies it, then I look at it again. If I look at it again, I'm going to get a different value. That is not repeatable read. Repeatable read says if I read it twice, I should get the same value both times. However, by the time I read it the second time down here, my other transaction committed. It's finished. And therefore, I am allowed in read committed to see the result of that transaction because it has already committed. And then finally, the 4th isolation level, read uncommitted, pretty much allows anything. If you are a transaction running in read uncommitted mode, any modification that anybody has made, whether or not they have committed their result, can be seen by reads that you do. So that means even if the transaction aborts and all of its modifications are undone, you could have seen what it did in the meantime. So an example being I read X here, I'm again T2, I read X here, and it's the value 6. I read X down here, and it's the value 10. And then maybe down here, this transaction suddenly aborts. And none of this ever happened. It's all undone, which means the value of X is actually 6 again when this is all said and done, because T1 never modified it. T2 would still be allowed to see the value 10 there. And another example, a non-destructive one, here we write the value 10 to X, and then I read it there. And then here I write the value 100 to X. So notice that in any conflict serializable case, T2 would either see the value of X up at the beginning, or it would see the value of X at the end, 100. It would never see this 10, because from the point of view of T2, T1 shouldn't be executing at the same time. But in read uncommitted mode, T2 can see anything that's happening, even if it's just rough work or intermediate results of a different transaction. So of course, read uncommitted is the least strict isolation level. And of course, we really shouldn't use read uncommitted for any transaction that might modify the database, especially if the modification could have implications for consistency. Read uncommitted can be useful if whatever you're doing, maybe generating queries for analytics or something, shouldn't be allowed to slow down the database or do any locking or something that might affect the speed of other transactions. So we've managed with only, 2 videos that I now have to edit together to talk about isolation. That's one of our 2 remaining big topics. And the other one is a discussion of how stuff is stored on disk in a database. And that's basically to talk about when we worked with databases in assignments 3 and 4, we noticed that some queries were really fast. And we should talk about how the database is able to store things so that when you make a query, it can actually figure out how to retrieve that information quickly, even if there are millions or maybe even billions of records in the database.